Okay, here we go. We've got a long list of things to talk about. We're going to have a little mini math class on imaginary numbers at the end of lecture today, or for the last thing we do in lecture. In case you forgot everything you ever knew about imaginary numbers, we're just going to have a little refresher on that. We're going to be talking about electromagnetic waves now at the end, by the end of lecture today, and we're going to finish chapter 23. We're going to skip an enormous amount of stuff in chapter 23. Okay, so we're in 23 now, and I think that's pretty much the extent of what we're going to do in chapter 23. Question? Your exam score, can it be the square root of -1? In other words, imaginary? Brandon, you already have one imaginary exam score. So if you have two, then that'll be the sum of two imaginary numbers, which is another imaginary number. So theoretically, okay, yes, we could do it if you want, but sweet. All right, what I want to do, by the way, you may have noticed I walked in without my walker today, very nice. And although my back is still pretty sore, but I was walking around all day yesterday at home, so I thought I'd try walking around campus today. We're going to take a look at homework 3. Now, homework 3 is not due until midnight, so if you still have attempts on it, you can, try one more attempt after we do it. But let's take a look at this one here. And this is a multiple choice question. From state P to state W in 0.25 second. Go ahead and make a decision. What direction is the induced current? This is the kind of thing you got to do on homework 3. And we'll talk about this one. It is open. Refresh your clicker. A biochem frequency. That's no good. Well, this is not biochem. $15 seconds starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Can you go make a count? All right. Let's see how you guys answered. Well, we got a little discussion to take care of here because we got a mix. All right. Let me move this out of the way. The correct answer, well, let's see. We go from a lot of inward field lines. We got 16 of them. And according to the key down there at the bottom, that's 16 Tesla meters squared of flux. And then from there we go to W, which is 5 Tesla meters squared of flux in a quarter of a second. So we're losing X's. All right, think of it that way. The current is going to want to produce more X's. It's going to flow. It's going to be induced in the direction that we'll put more X's in there. So that's going to be, according to the right-hand rule, clockwise. Look at my hand. All right? Look at my hand up here, my right hand. Clockwise into that screen. All right? So the correct answer here is A. And let's see, I can grade this one. The majority of you got that, but a bunch of you didn't. So make sure that when you're doing your homework, if you try another homework, eating Chick-fil-A breakfast in here. Right? And I always look in that direction too. Is this a ruse to trick Dr. B into, you know, it's all right. I'm not hungry. Anyway, so when you're doing, if you have another attempt on homework 3, you can get this part right. Emily. Right. The explanation is, first of all, you go with the right-hand rule. Now, induced current, well, any current in a loop, okay, if your hand is the loop, then your thumb is the direction of the field in the middle of the loop. Okay, so now in this one, you're losing X's, which are going into the plane of the display. All right, so you want to get more X's from the induced current wants to put more X's back. All right, so the X's are the thumb. So Emily, if your thumb is pointing into the display like that, that's what the induced current is going to do. Then your right hand curvature here tells you the direction the current's going to go. All right. And so that's how you figure out that it's clockwise. Okay. Another question. Yes. What is your name again? Christine? Okay. No, X's mean into the page. Look at the diagram. Right. The X's mean they're going into the page. The circle with the dot in the middle of it means they're coming out of the page. Okay, now I've got this all in terms of X's. And so what this means, Christine, is I've got a lot of X's. State P is a lot of X's, a lot of these. Right, so the north pole of the magnet is fairly close to the loop and out here. You know, so the N pole is here, the S pole is here, back here, and it's fairly close to the loop. So you got a lot of X's in state P, but now state W is you bring it back a little bit. You lose some of those X's. Now what that means is that it feels not as, the average strength is not as intense. All right. CJ. If we went from W to P, right, which you could do, you know, you start with the magnet way out here and you bring it in close to P, getting P, then yeah, then you'd want to defeat these ones with some of these ones out of the page, and then that would be counterclockwise. All right, so yeah, it's tricky to, you know, keep all this sorted out, but your right hand rule, and you know, and think about other, you know, complicated circuits. This is a circle. This is about the cinchiest one there is. Let me ask you a question. Clockwise or counterclockwise? Let's assume clockwise. How do the wires on opposite sides, like 9 o'clock and 3 o'clock, how do they interact? Because they're both current carrying wires in a magnetic field. You know, so the 9 o'clock section of wire over here at the 9 o'clock is creating a field over here at 3 o'clock. And so the 3 o'clock wire is experiencing current going through a magnetic field. By the same token, the 3 o'clock wire over here is producing some field lines over here at 9 o'clock. So the 9 o'clock wire is also experiencing current going through a magnetic field. So how do those wires interact? Two wires, just those two. Think of only those two. Let's abstract everything else away. Are they parallel currents or anti-parallel currents? 9 o'clock versus 3 o'clock. They're anti-parallel. You know, one's going uphill and the other one's going down. Okay. At that point. Now, if you were to take the points at 12 o'clock and 6 o'clock, they'd still be anti-parallel. Okay. If they're going clockwise, it would be like this. Okay. 12 o'clock would be going to the right. 6 o'clock would be going to the left at that point of the circuit only. Anti-parallel wires, what do? Attract or repel? They repel. Better remember that. All right, let's do another clicker question. And hit the refresh key because this is going to be numeric. And for this one, just calculate the size of the induced current. Okay, great. Great, thank you. We have an awful lot of absentees. That table's half. Yeah, type in a whole number and then click the send key. One minute, starting now. This is not a difficult calculation. It shouldn't take 2 minutes, you guys. This means I should go look at the, could you log it? No, you can't do it. Thirty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's take a look at your guys' answers. Yeah, so all you got to do is calculate, it's one loop, so n is equal to 1. Delta phi over delta t, so it's later minus earlier. So it's 5 minus 16 Tesla square meters. So that's minus 11 divided by 0.25 seconds. That's delta t. So that works out to 44. So let me make this a little bit bigger. Let's take a look at your answers. For those of you that typed in 11, that is wrong. That's the change in the flux, minus 11. Here, 18, ooh, that's twice as high as it should be. So you got to figure out, because we only have one loop, so whoa, 0.44, I don't know how you get that. 120. Wait a minute. 16 plus 5 is 21. 21 times 4 is 84. So do we see any 84s on here? So sometimes I can kind of semi-figure out a wrong answer. No, there's no 84s on here. There's a 42. I don't know. Some of you guys have a factor of 2 in there that doesn't belong. Anyways, 44 is the correct answer on that one. All right. So go ahead and make a note of that. Now, my last word on this is simply that does anybody want more attempts on homework 3? If you've burned off a few, I could put another 2 on there. So if you've already burned off all 4, unwisely burned off all 4 of them. All right, so I'll put another 2 attempts on. I'll try to do that after class, I guess. All right, so you can do another 2, but it's still due at midnight tonight. So, all right, now let's go and talk about inductance. Now we've been dancing all around this topic. Inductance is a circuit concept that we're going to really look at carefully today. Now, we're not going to get all fancy up into AC circuits and reactants and stuff like that, phasors and stuff. Sometimes I go through that, sometimes I don't. But I'm going to just do a little bit about inductance. Now, here is a diagram from 23.9. This is a pair of coils, one inducing current in the other. So coil 1 has a changing voltage source. So the current is changing. That little circle, that fluke symbol with a squiggle in it, that means that's a symbol for alternating current. Okay. So you've got a rightward pointing field and then a leftward pointing field and then a rightward pointing field in coil 1 from that current. Now, coil 2 is in there close enough that it's going to get it's going to catch and uncatch some rightward field lines. It's going to catch and uncatch some leftward field lines. All right, so it's going to get induced current, and the galvanometer down there is going to measure that. All right, that's kind of what we were talking about last week. Now, coil 2 and coil 1 might be really efficient, all right, for inducing current in coil 2. All right, and that efficiency or that property of the circuit, you know, where it really is effective at producing more electromagnetic current is called inductance. And there are 2 kinds of inductance. And what we've got here in this diagram from one coil to another, that's called mutual inductance, M. And it depends on the geometry of the circuit, what the circuit is made of. You know, does it have an iron core? Does it have a plastic core? Does it have air core? You know, what, you know. And the symbol for an inductance in a circle is a curly Q, a little coil. Although they use kind of a half-baked symbol in our textbook, kind of a half of a curly Q. But I usually use curly Qs on my sketching. Now, a coil can have inductance with itself. That's called self-inductance. So, you know, a coil, as current changes, the field will get stronger, and the coil will feel that and try to, you know, whatever the current, you know, whatever that current source down there, that fluke with the squiggle in it, whatever it's doing, the coil will try to oppose that. That's self-inductance. All right. And self-inductance can lead to some disastrous effects. Self-inductance is a way of kind of tempering the changes in the current, not the current level, but the changes in delta I over delta T specifically. All right, so delta I over delta T is of utmost importance in this because it turns out that that's the source of the inductance. Okay, in the in the EMF. In both kinds of inductance, the EMF drop or gain is dependent upon more field lines or fewer. Okay, or another way to put it, more flux or less. Changing flux, more flux or less flux. And that means in a circuit, that means increase or decrease of current in a certain amount of time, so per second, delta T. So delta flux over delta T, that's Faraday's law. Field lines, delta field lines over delta T, that's kind of an old-fashioned way to look at it. That's how Faraday looked at it. But in reality, in a circuit, it's really, because the induced current is dependent upon the excuse me. I needed more sleep last night watching the Packers game. So in a circuit, you would think in terms of delta I over delta T, change or decrease in current. All right. Now, we're going to go to the document cam, and we're going to calculate an induced EMF. So could you operate we got that. Let me try to move myself over here. What I found is that my back rebels against these certain chairs are extremely uncomfortable for my back. This one's not too bad. All right. We're still recording good. All right. Could you go grab me a couple of pieces of blank paper? Thanks. Okay. Here we go. All right. So the delta V EMF in an inductance is minus L, and we'll do the self-inductance, times delta I over delta T. Okay, so there's the definition of the EMF, and it's similar for mutual inductance between two separate circuits. But we're going to try to work in one circuit today. Now let's calculate the induced EMF in a circuit. And actually, let's do, let me put in the mutual minus M over delta I delta T. So that's the basic idea of inductance. Oh, by the way, let's look at the units before we do the calculation. Volt is equal to the units of L times delta I. So that's amperes, and delta T is in seconds. So the unit of current, or excuse me, the unit of inductance, which is called the Henry, after Professor Henry from Princeton, who discovered a bunch of this stuff about the same time as Michael Faraday. It's volt second per ampere. All right, so that's the unit of inductance. And that's also equal to a bunch of joules and stuff, Newton meters and junk like that. You convert it to newtons and joules and stuff if you want, but we're gonna do this for now. Okay. Now here's our calculation. We're gonna have two circuits, and here's one inductance, and we'll connect it to a fluke and a switch. Okay, so there's my switch. And then we're going to do another inductance, and let's say that they have the same mutual inductance. Okay, and this one is conducted to a fluke. Okay. And let's say that M is equal to 5.00 millihenries, little m subscript h. All right. And let's say that the current here in number 2, it goes from 2.00 amps to 0.00 amps. In other words, it goes to 0 in delta t equal to 3.00, no, scratch that, 30.0 milliseconds. All right, so now let's put together our EMF. EMF is equal to minus M, and I'll just rewrite the delta I over delta T. And it's just kind of a cinchy plug-in. So this is equal to, all right, minus 5 milli. So this is 5.00 times 10 to the minus 3 henries. That's a millihenry. And we'll eventually use this conversion up here in order to get, see how we're going to get volts and amps out of this? We're going to get volts in the end for the EMF. All right, now delta I over delta T is final minus initial. So this is 0.00 amps minus 2.00 amps. There's my delta I. And then my elapsed time is 30.0 milliseconds. So that's 10 to the minus 3 seconds. All right. Now I'm going to convert the henries. I didn't do it in my scratch paper, but I'm going to do it here. I'm going to keep the same numbers here, times 10 to the minus 3. And instead of a henry, a capital H for Henry, I'm going to change it to this business up here, volts seconds per ampere. All right, because I'm going to start canceling. Volt second per amp. All right, so there's my inductance. All right, and I still have, now over here, my quotient is negative 2.00 amps, and I still have 30.0 times 10 to the minus 3 seconds. All right, now the reason that I did that is so that now you can see the cancelization. All right, we got seconds down here, seconds up here in the inductance. Bam, they're out of here. And Jenna, we got amps down here and amps over here. Okay, so they're out of here. But we still have volts, and that's good because we're looking for an EMF. All right, now the other thing, anything else you think I should cancel out of here? What? 10 to the negative 3, why not? Yeah. Let's cancel this baby out. You can't always do that, but in this problem, yeah. All right, so I've got Dude, 10.0 on top, volts, divided by 30 on the bottom. And so that's equal to a third, 0.333 volts. All right, so that's a household size current, amps, millihenries for inductance, that's some kind of a coil in your circuit, and a household size of volts. Okay, that's what we would call a back EMF. Thomas.
Did we just disregard the negative sign?
No, we canceled it. We can't. I mean, it doesn't really matter. We're just calculating the magnitude of this. But I had a minus sign here in the delta I, and I had a minus sign out front from Lenz's law. That, by the way, that you guys up here in these two calculations for EMF, the minus sign is from Lenz's law. I mean, they're basically an application of Faraday's law. And the minus sign in Faraday's law, delta flux over delta T, is from Lenz's, so basically an oppositional minus sign. Anyway, so there's my calculation. All right, and this example is problem 2 in chapter 23.9. So if you want to go look that up, you could definitely do that. All right. Now I want to go back to the projector for just a minute. We're going to follow up on this. We're going to do some more with these kind of circuits. But before we do that, I want to. Okay, can you switch to laptop, please? I want to talk about something that we didn't have in that previous circuit. We didn't have a battery or a resistance. Now, this is a special kind of a circuit. It's called an RL circuit. And what we're going to find is that it leads to exponential decay and exponential growth, specifically the loading or the saturation curve. All right, so we're going to take a look at that, and that's for an RL circuit with or without a source. Matter of fact, the way that this one would work, when switch is switched to number 2, when switch is switched to number 1, the maximum current is going to stabilize at some level, and you're going to have energy stored in the magnetic field of the inductor L. See, there's a symbol, the semi-curly Q symbol of the textbook for an inductor. Okay, so when it's switches at 1, it loads up current into the inductor. When you switch to 2, the current will dissipate its energy at the resistance, and that's what you see over here in the exponential curves. So let's take a look at the document cam. Go ahead and switch back. And let's do another page. Oh. All right. So for an RL circuit, okay, delta V is equal to IR at the resistor. Okay, that's Ohm's law. Now, at the inductor, delta V is equal to, and we'll use a self-inductance, minus L times delta I over delta T. Okay, so that's the inductor's opposition. Okay, so that's at the coil or at the inductor. Okay, there's no battery. So the loop equation is simply this. 0 battery equals minus L delta I over delta T plus IR. All right. And if you look at that carefully, you'll see that IR is equal to L times delta I over delta T. And we can do one more move here, get the R over to the other side. And that is I, and I'll put it I of T equals L over R. Those are both constants. And then delta I over delta T. All right, now I want you to look at this equation carefully. Tell me something about that equation. Analyze that and give me some physical insight. You can get any number of engineering majors to do all your calculus and your trig for you and get all the equations you want. But what do they mean? It's the law of currents. Implicitly, it tells you how the current changes over time. What else does it tell you? Abby, you're looking at me over the screen there. What else does it tell you? Come on. It's got exponential time dependence. Right. And that's why we just looked at that set of curves. All right. Right. So I of t is either going to be I of 0 times e to the minus alpha t, or it's going to be I max times 1 minus e to the minus alpha t. This is for loading, and this is for discharging. But it's not a capacitor discharging, it's the coil. The coil is discharging its magnetic field. All the energy stored in the coil is doing work at the resistance. All right. So you have either one of these. And as I've said before, whenever you see a delta something over delta t proportional to something, in this case I of t, you've got exponentials. All right. And in this case, alpha is equal to L over R. Matter of fact, let's just double check this. Let's check the units of alpha. Okay, so it's equal to henries over an ohm. And let's see, a henry was what? Volt second per amp. And let's see, V equals IR. So R is V over I. So volts, I always have to look up ohms. So ohms are volts per amp. So 1 over ohm is amps per volt. So alpha is seconds. That can't be right. I made a mistake there. Volt second per amp. Okay, so this should work out to, so let's make our alpha R over L. So R over L is going to be seconds. Okay. And so this is, or seconds to the -1. So so that your time constant is tau is equal. The time constant is R over L, or L over R, and alpha is 1 over that. Okay. And so the time constants are in those diagrams. Can you move to the next slide? Okay. All right, now let's do an inductive circuit with a capacitance. And we'll ignore the R for the moment. Okay. Now, delta V for a capacitance is equal to the charge load on the capacitor divided by the capacitance C. Okay, and the delta V in the inductance, we already know what that is, minus L times delta I over delta T. All right, and that's in the inductor, in the coil, or whatever inductive device you have. Now, a couple things about delta I over delta T. I is defined as delta Q over delta T. All right, so this thing in here, delta I over delta T, that's actually the delta of this stuff. All right, so now, don't let me trick you. I'm not trying to trick you. I want to make sure that we do this very gingerly. I'm going to write this down as delta squared Q over delta T squared. All right, and that's this term right here. And that's because this is my I. That's the formal definition for I. All right, and that's delta V for the coil. All right. Now let's look at the loop equation. No battery. So we're assuming, Rachel, that we're going to charge up the inductor and the capacitor with a battery, then switch the battery out of the circuit so that these guys can discharge through a resistance. Now we're not going to bother with the resistance for now. We're just going to look at these two guys unopposed to a resistance. All right, so let's just look at the loop equation. Okay, so no battery, 0, equals, okay, 1 over C times Q of T minus L times delta squared of Q over delta T squared. And now what we've got, now we're going to, as I said before, the whole idea with this stuff, and for these guys that are trying to go to med school and stuff, it's not enough to memorize tables of data. You want to think about what's actually happening. What does it mean? All right, now let's look at this. Yeah. What's this? These are the two delta V's in the loop, the capacitor and the coil. Okay, so this is 1 over C times Q. All right. So the capacitance drop is here. All right. The coil drop is here. Okay, now we started the coil drop out as a current delta I over delta T, but I tricked it out as this weird looking double delta. Chris Montez, this is delta squared Q over delta T squared. For those of you that have had calculus class, raise your hand if you've had calculus class. You notice anything? Derivatives. What's that? What kind of a derivative is this? Second derivative. All right. Yeah, because it's the second time you do a delta T of it. Think of it that way. So, shh, 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 shh. You guys, listen carefully. So what we're doing here is we're kind of whistling past the graveyard, so to speak. The graveyard known as calculus. We're kind of walking along, and we're trying not to get too scaredy of ghosts and stuff in the calculus graveyard. But this is a little calculus here. All right. And Q of T. Now let me ask you this. Let me give you an analogy. You know, you're trying to figure out the meaning of all this. Let's use an analogy. Instead of putting Q of T, let's put position X of T as a function of time instead of Q. What would delta Q in this analogy over delta T, what would that be analogous to in the analogy? Speed, delta X over delta T. All right? All right. Now, we don't have that. We don't have an I in our loop equation. We have a Q and we have a delta I over delta T. All right. But if we did have a Q, an I, you know, if we had a resistance in the circuit, you know, we'd have some, it would look something like that. All right. Now, so there's my analogy. If Q of T is like position as a function of time, what would this be like in terms of the equations of motion of an object? You know, so in terms of Sir Isaac Newton type equations of motion. Delta Q over delta T would be like delta X over T, the speed. So what would this one be like? Acceleration. All right? All right, now let's extend the analogy. What kind of a an equation? Does anybody see what kind of equation this looks like? This is the analogy now. Okay. This position, and it's equal to something times the acceleration. You know, have we ever seen anything like that? Second law? Yeah, F equals ma. All right. So we've seen a ton of those. F equals ma. That's all over the place. Sir Isaac von Newton. All right. Now let me. So all right. So okay. The A term, which corresponds to my delta I over delta T term here. That's this. My inductive term. Okay, that reminds me of F equals ma. Do we ever have a force that's dependent on X? Do you ever remember anything like that from, huh? Yeah, spring force minus Kx. So we have a spring force equal to an m, and we could write it this way. We didn't do it, but we could have. Delta x squared over delta t squared. And that's a spring force equation. Now, what happens with springs? It's oscillation. Oscillation, 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 oscillation. I can't go any further than that. My voice is, I can't get higher. I used to be able to get higher than that. But. So, my wonderful students, can you move this to the next slide, please? I'm already way farther than I want it to be. Okay, that's good where it is. Okay, so oscillation. Let's write an oscillator expression. Now, it's not going to be exponentials, okay? But we can write it this way. And I'll use lowercase q. Q of t equals q of 0 times cosine of some frequency omega times t, or q of 0 times sine of some frequency omega, and omega depends on, remember what omega depended on for the oscillator, the spring potential? It depended on K and M. So for the inductive circuit, it's going to depend on, so this is the analogy here. All right, so it's going to depend on C and L. So omega depends on C and L for the LC circuit. And that, my wonderful students, is how we generate radio bandwidth. Yeah, the stuff that goes like this electromagnetically. Oh, I got an visual IQ test for everybody. I'm going to stand up here. Let's see if I can stand up. All right, now this is something I learned when I was a physics major. Way back in 1846. Okay, so see this? What is this? No, you're supposed to say, I don't know. I don't either, but here it comes again. So that's a joke you can tell like the sixth graders, but I wasn't very smart, so it took me until I was like a senior in undergraduate physics major to get that one. Anyway, now let's go back to the display here. Kendra, would it be possible for you to sit over here and help me instead of sitting over there?
The laptop?
Yeah, please. All right. Hey, Nika, what's this? I don't either, but here it comes again. All right. I have a very limited amount of jokes. Well, like, okay, what do you call a pot of water boiling on top of Mount Everest? You give up? A hypotenuse, high pot in use. I learned that in 10th grade. What do you call, what did the Acorn, wait a minute. Oh, what I had to go back into the memory circuits. What did the acorn say when it grew up? Gee, I'm a tree. See? It's pretty bad, huh? This concludes my comedy spiel. That's all I got. All right, let's take a look at this. Now in about 1880 or so, Professor Hertz over in Germany figured out an experimental device to observe um, electromagnetic waves. They had figured out by then that electromagnetic waves were possible. The mathematics was perfect for oscillating electric and magnetic fields that propagate through space, but nobody had figured out a way to observe them. So what he did was he set up two um, different loops, a transmitter loop and a receiver loop. All right, and he set up an LC circuit at a specific and there's the formula for. Go ahead and write down that formula for the frequency. 1 over 2 pi times the square root of LC. Okay. And he said, all right, let me set that to so many cycles per second. I don't know if it was 100 or 2,000 or what. So he built a capacitor, he built a resistance, he built an inductor to basically a transformer, and he hooked it up to this loop. Okay, now the loop was designed to cause a spark. It wasn't connected, but it would have sparks at a certain frequency. All right, and those would generate waves of a certain frequency. If the circuit has a frequency and you juice up the transformer high enough, it's gonna start clicking out sparks. Just like this. At whatever frequency he has it set. Now, his tuner over there was set up on the other side of the lab. So like from here over to the other side of the building, he had a tuner. And by God, he picked up the sparks over there, the same frequency. And that was the first measurement of the propagation of electromagnetic waves. It really was true. And he proved that it diffracts just like light. He proved that it's just like light and that it actually is light. All of light is electromagnetic oscillation. And we now know, everybody in this room, and put an L and a C on a circuit and bang, you can do it too. And all of our communication gear is based on this simple circuit here. And in fact, zillions of them and bozillions of them inside your phone. The clock on your phone. It's got an oscillator in there. Ding. Everything. They do some variation of this kind of a circuit, an LC circuit. Encryption, that's math. Encryption works, that's a mathematical, it's arithmetic. Well, depending on the encryption, method. But that has nothing to do with oscillation, so far as I know. But what they do is they do frequency hopping so that you get a little bit of a signal. And if both receivers know the frequency hopping algorithm, that it's just changing position. They catch each other at each frequency, but your eavesdropper doesn't. That's how that works. That's more like masking. It's not really encryption. Okay, so LC circuits, we now have everything that we know conceptually to understand electromagnetic radiation. How Professor Hertz first observed it, and how anybody, lasers, they got this kind of stuff at the wazoo in a laser, because what they like to do with lasers is shoot them in pulses. A pulse lasting 10 to the minus 12th of a second or even smaller. Oh my goodness. But they do it with stuff like this. All right, now, here's a discharging capacitor. All right, now remember we did this? All right. And that the half-life is right here. And that's my numerical approximation. I'm a little bit above halfway. I'm a little bit, on this curve, I'm a little bit late getting to the halfway point. Now, the time constant in an RC system is where it's not the half-life constant, it's where the current drops to approximately 36.8%. All right, halfway is the half-life. It involves the logarithm of 2 and everything. RC is simpler, but it's not a simpler percentage. That's the 1 over E drop time. So that's approximately 1 over 36. It's approximately 36.8%. So the half-life is tougher to calculate with logarithms and stuff, but it's based on the RC time constant. So, and the half-life is where you get down to halfway from where you started. Right, and we've done this already. Exponential decay. So here's the 1 over E level. That's a 36.8 level, and this time constant down below is the time scale is tenths of a second. And so you can see that my curve is a little bit late to the 1 over E level as well. It's supposed to be right there where that black arrow is, but it's a little bit late. Now, here's the loading curve. Now, these also apply, as I said, to the LC circuit, or the LR circuit. All right, that inductance is going to load up with current, and eventually it'll stop loading. All right, it'll oppose further loading, but it asymptotically gets to the maximum load, just like a charging capacitor loading up. Now, remember this. Now, here's something I want to point out to you. All these circuits with R's and C's and L's and RL's and LC's and stuff, they're either exponentials or they're sines and cosines. All right? And there's a reason for that. All right? Now, I'm going to go over the reason for that with you in the next few slides. Here we go. Imaginary numbers. So this is our little mini lecture on imaginary numbers. All right, here we go. The imaginary number, if you have forgotten, it is the number that has this property, I squared equals minus 1. Now, in 6th grade math class, you know nothing of, and you might know squares, but you don't know of any squares that are equal to a negative number, because every integer squared is positive. Negative 17 squared is positive 289. Positive 17 squared is positive 289. But somebody, I think, who was it that invented this? Euler? Somebody invented the imaginary number I, and it's with this property, and it gives us the ability to deal with imaginary square roots. So if you have like a quadratic equation for which the answer has a square root of minus 18 in it, you can handle it. Here's how you do it. Square root of minus 18 is equal to minus 1 square rooted times 9 square rooted times 2 square root. So we're breaking it out into square roots, a product of square roots. Now that minus 1 square rooted turns into the imaginary number I. So just park that out there to the front. Now we know what the second one is. Square root of 9, that's cinchy. That's just a 3. And square root of 2 is square root of 2. Nothing to do about it. I mean, it's just may as well leave it that way. So your answer here is basically I times 3 times the square root of 2. And here's the more streamlined way of expressing it. 3 square roots of 2 times I. Now, some equations that you run into, they come up with imaginary numbers for the solution. So for instance, x squared plus 2x plus 2, that's algebra class from 9th grade or 10th grade. Do you know what? I took algebra class, algebra 1, when I was in 11th grade. I was not in advanced algebra or anything. A bunch of you guys probably took algebra 1 when you were freshmen. See, but not me. I had to work my burp off to get through all of my math classes. So for equations like that, they only make sense if you combine regular and imaginary numbers, or real numbers and imaginary numbers. And that's what we call complex numbers. Okay, so for instance, -1 plus I and its complex conjugate, -1 minus I. Those could be a solution. All right. And just go to algebrahomework.com or whatever, and you'll find buku problems like this probably, or maybe trighomework.com or any site like that. That's a quadratic. I mean, everybody in here probably remembers trying to factor stuff like that, factor trinomial in high school. You know, the FOIL method, first, outer, inner, last, all this stuff. I see some of you smiling. I see other people shaking their head like, no, Dr. B, no, not any more of that. And in fact, we're not going to do that. But what I want to do is a little bit of complex number working out with you on the dot cam. So let me move over here. See if my back will permit it. And let me get a piece of papyrus. Could I get another piece of paper?
Yes.
Oh, you know what? I'm going to take a time out, and I want to go backwards in time. Ooh, complex numbers backwards in time. Yes, they are related. Time travel. You're so lucky to have me for an instructor. LC circuit. Can you switch to the dot cam, please? I want to talk about LC circuits just for a little bit longer. Energies. Okay. So energies. Now, for the capacitor, the energy in the capacitor was equal to 1/2 times 1 over C times Q squared. All right, now that was from chapter, I don't know, chapter 19 or 20, somewhere in there. All right, and we didn't do a whole lot with that. I think we maybe did one problem with that. All right, but now we also have an inductor. So the energy of the inductor has a very similar form. It's equal to 1/2 times capital L, the self-inductance, times I squared. Now, let's remember the who is talking over here? Please stop. You're distracting me and you're distracting your neighbors. Don't talk on top of me. Sorry I have to yell, but sometimes you guys don't get it. All right, now let's do this analogy. Energy in the analogy proportional to, this would be x squared. Energy proportional to x squared. Now, what was I the equivalent of in the analogy? We kind of bypassed it a little bit. Remember what I was? Delta Q over delta T? What was that analogous to? Look at your notes. V. So where do we have a system, a physical system, where we have energy proportional to x squared and v squared? It starts with the letter O. Oscillation, oscillation, oscillation. Total energy of the oscillator. 1/2 kx squared, 1/2 mv squared. Mm-mm-mm-mm. Mm-mm-mm-mm. The energy equation. Therefore, one more way to see we have oscillation in the LC circuit. Mm-mm-mm-mm. Okay, so if there's, all right, so I'm screwing around up here, but for singing, but this is, as I said, a very important result. Now, the constants look a little bit different. It's 1 over C, 1 over L. Oh, no, this is not 1 over L. This is just regular L. Okay, so there's the energy equation for an LC circuit. And Q is the charge load on the capacitor. You just got to remember that. All right. And so that's analogous. That is exactly analogous to the spring system up here. Exactly analogous. All right. So I just wanted to point that out. So we already had a restoring type force situation. You know, this is a restoring force in a spring system. F equals minus kx gives us oscillation. And here's the other sign. Whenever you have a coordinate and the square of a coordinate and the square of the change in the coordinate per unit time, quantity squared, then you have oscillation. That's the spring system. So that's why the spring system is so useful. And as a matter of fact, we use some very fancy, what we call analog circuits for things that I can't tell you about. So I'm just going to put a block here. I'm going to redact it. But we use analog circuits for very important stuff that tends to get redacted for civilians. But it's important. And it's based on this analog. And it's not really, and students, it's not an analogy anymore. It's exact. It's a thing. It's true oscillation. All right, now I want to get back. Can I get another piece of papyrus?
Yep.
To imaginary numbers now. Thanks. Imaginary numbers. Okay. And what was the equation that I had written down? Can you go backwards for just a second? The backwards key. Okay, go forwards now. One more. One more. Keep going. Go. Go. Okay, that's it. X squared plus 2x plus 2 equals 0. Okay, go back to the, keep going. Go, stay there, stay there. Go back. Go to stay there. Okay. All right, so imaginary. Now, here's a little equation. The solutions are, let's see, minus b plus or minus the square root of b squared minus 4ac over 2a. And a is equal to 1, and c is equal to 2. So this is minus 2 plus or minus the square root of 4 minus 4 times 2 times 1. That's not right. 4 minus 8. Oh yeah, I guess that's all right. And 2a is 2. So this is equal to minus 2 plus or minus the square root of minus 4 over 2. So there's where my negative square root, I think they call that the radicand in the math department, the stuff inside the square root. So this is, but it's definitely got a 2 in there. So this is minus 2 plus or minus 2 times the square root of minus 1 over 2. And that's equal to negative 1 plus or minus I. Okay. And so those are the solutions to this equation. So this equation is true wherever x is equal to negative 1 plus I, or negative 1 minus I. So you have to graph that out on the complex plane. All right. So this is the real axis. This is the imaginary axis up here. And you just use it like x and y coordinates. So both of these are at x equals minus 1. So let's go, here's 1, here's minus 1. This is 1i, here's minus 1i. All right, so here's your two solutions right here and right here. All right. Now, something I want to show you about this. Let me put a dot out here for 2. All right, and let me put a dot up here for 2i. All right. Now, how do you get 2i from 2? 2 multiplied by I is 2i. All right, so multiplication by I here is the same as rotation by 90 degrees. All right, so draw in, let me use my red. So this rotation from here, from 2 all the way up to 2i, that 90 degree rotation is geometrically equivalent to multiplication by I, square root of negative 1. So that's a geometric equivalence. And that is the difference, my wonderful students, between having exponential decay and oscillation. The only difference is that with exponential decay, the time constant tau is a real number. But in oscillation, the time constant is imaginary, rotated by 90. And so this is also called the Wick rotation, and it is how we figure out quantum tunneling in quantum field theory, and also how we figure out the one of the tools we use for figuring out the geometry of black holes. So that's why this is When you see this stuff, that's why you can say that it's important. This whole idea of, well, what do we have? Decaying exponentials, or do we have oscillating exponentials? Because that's what it is. When you have sines and cosines, it's oscillating exponentials. It's imaginary time constants. It's a difference of 90 degrees. Now, let me go back to the here, and let's finish class. Here's another. Here's another diagram. So here's one of the roots of that quadratic equation. And -1, 1, that's where you graph it up. And that 90-degree rotation is what converts exponential decay into sinusoidal oscillation. So go ahead and write this down, e to the minus t. If we have a different situation in which that frequency or that time constant comes up as an imaginary, i.e. e to the minus it, then if you may remember this from trig class, you might not. It's called de Moivre's theorem. E to the plus or minus I something is cosine of something minus I sine of something. And that is how that is why you say complex exponentials bring in oscillation, because of this theorem. All right. So this whole idea of resistors, L's, inductances, and capacitances, it's all tied up in this thing of these imaginary numbers. All right. Now we're not going to. We could do a huge amount of circuitry work with AC circuits and all the complex numbers embedded in them. Who's that guy that was in favor of alternating? Tesla, Nikola Tesla. This is child's play to him. You know, he was the guy that figured out all this stuff for AC circuits, and he was and that's why we have alternating current in our homes and shops and buildings and stuff now, because of Nikola Tesla. But it's all tied up in this. And here's the exact analogy. Go ahead and, this is not a diagram in our book, but go ahead and make a note. You know, the potential energy in the spring is like, and see, this one uses a spring-like symbol for the inductor, and he uses parallel plates for the capacitor. And you can see that it goes from a lot of energy stored into a lot of energy in use. The kinetic energy term is the inductance term. All right. Now, we wouldn't say it's kinetic energy in the inductor, but we would call it the kinetic term because it's like a kinetic energy in a spring system. And so make a note, this kind of analogy of the spring system with an LC circuit is exact. It's an exact analogy, and it's a very serious one for us. Now, I was going to give you a little bit more instruction, but I think I'll stop here. I want you to, for your reading tonight, make sure you finish homework 3, study 23.9 carefully, and then skip ahead to chapter 24 on electromagnetic waves, and you'll read about Hertz and stuff in there. We'll start with chapter 24 on Wednesday. You're dismissed.